Hello. I'm Bretton, one of our MCAT tutors here at Inspira Advantage, where I help students get to medical school and other professional programs. And welcome back to MCAT Bites. In this episode, we'll be discussing carbon-13 nuclear magnetic resonance, or 13C NMR spectroscopy. A lot easier to say. This is another essential tool for figuring out the structures of organic compounds. While 13C NMR is not as commonly tested on the MCAT as HNMR, understanding its principles and applications will give you a more comprehensive grasp of spectroscopy. And there will still be a couple questions asked about carbon NMR spectroscopy. Let's start with the basics here. 13C NMR spectroscopy is based on the same principles as HNMR, but instead of focusing on hydrogen nuclei, it's measuring the absorption of electromagnetic radiation by carbon-13 nuclei. Carbon-13 is a stable isotope of carbon that makes up about 1.1% of naturally occurring carbon. When placed in a strong magnetic field, carbon-13 nuclei absorb radiation at different frequencies depending on their chemical environment. For example, in this image, the different chemical environment are the different amounts of hydrogens. So down here, these are just single carbons. Up here, we have a carbon with two hydrogens next to it. Or here, it's coming up a bit blurry here. This should be CH chlorine. We see a different shift, and this is a CH3 and a CH3. So even though the carbon is bound to the exact same thing, right? This is literally next to three hydrogens. This is literally next to three hydrogens. It's still at a different part on the spectrum. And that's due to not only what is right next to the carbon, but what is down to it a bit further away. You should be familiar with the key features of 13C NMR spectrum and how they relate to the structure of organic compounds. You don't have to worry too much about de-shielding for the MCAT. That was a fancy term used in Orgo. We're not going to worry about that too much right now. We'll talk more about that for HNMR, where they're going to test you more on that. The main features of the 13C NMR spectrum are the alkanes, which are found from 0 to 50 ppm, down in this region, alkenes, alkynes, and alcohols. The alkanes, which are found from 0 to 50, which is in this region. And I want to note that this is actually kind of flipped, right? So 0 is on this side, and the numbers get higher as we move to the left. So the right is lower, which is just a weird way to think about it. So alkanes, 0 to 50. Then alkenes, that's a double bond. Alkynes, triple bond. And alcohols are from 50 to 80. So we can think about it as we're getting more saturated, we move more to the left here. Then we have our aromatic compounds from 100 to 150, just kind of this general area. Then 160 to 180, we've got carboxylic acids and our esters. And then finally, 190 to 220, we have our aldehydes and ketones. And this is sort of loosely corresponding to oxidation states, right? Like an aldehyde and ketone is not as oxidized as our carboxylic acids, but overall, the more oxidized groups over here are further along than the alkanes, which are less oxidized. So that can kind of help you when you're in a guessing situation on the MCAT. But I would recommend just putting these into your Anki cards and making sure you've got it memorized. And just to speak on what is this ppm thing at the bottom a little bit, well, it's showing a delta. It's like in HNMR, the chemical shift in carbon-13 NMR is indicating the position of the signal on the x-axis measured in parts per million. However, the range of chemical shifts in 13C NMR is much, much broader, as we just saw, spanning from 0 to 220. The chemical shift provides information about the electronic environment of the carbon atoms. As we saw, carbon atoms in different functional groups will have characteristic chemical shift changes, the alkanes, alkenes, etc., etc. So now we're going to move to the signal number, which is also important. The number of signals in a 13C NMR spectrum correspond to the number of unique carbon environments in the molecule. So each chemically and magnetically distinct carbon atom will give rise to a separate signal. This information helps you figure out the symmetry and complexity of the molecule. So if we look at this spectrum here, we can see there's 1, 2, 3 different vertical lines, meaning there are 3 unique carbon environments. And if we look at the true structure, that makes sense. This CH2 is different from this one because this CH2 is closer to the hydroxyl group, whereas this CH2 is next to a CH3 and a CH2. And then on the end here with the CH3, which, because it has an extra hydrogen, is chemically distinct from the other 2, meaning it makes sense. So we have 3 different peaks. But the chrylate has 6 peaks, 1, 2, 3, 4, 5, 6. But if we're looking really closely here, we'll see there's only 5 carbons in the molecule. 1, 2, 3, 4, 5. So where's the 6th coming from? And I say, let's look at the weirdest looking one, which is definitely this. and it's difficult to read, so I'm going to write it out here a bit bigger, but this is actually CdCl, which is a solvent. That means we ignore this, and it doesn't matter. Another giveaway is that it's a pretty low peak, so that means there's fewer carbons with it. Finally, before a little bit of practice here, let's talk about signal intensity and splitting patterns. So for signal intensity, unlike H-NMR, the signal intensity in 13C NMR is not always proportional to the number of carbon atoms contributing to the signal. The intensity can be affected by factors such as nuclear overhaul, Overhauser effect, NOE, and relaxation times. As a result, 13C NMR spectra are typically recorded under quantitative conditions or with the use of additives to minimize these effects. So as we can see in the example we just looked at, we found all 5 carbons present in the molecule, but clearly there are different amounts. And if this were H-NMR, we'd say, well, these 2 carbons must be half as common as whatever these are. We see the proof. It's not true for carbon NMR. So we want to be careful making any claims about the intensity based on just a carbon spectrum alone. Now for splitting patterns, 13C NMR signals do not typically show splitting patterns due to just the low natural abundance of carbon-13 atoms. However, in some cases, splitting can be observed due to coupling and neighboring protons or other carbon-13 nuclei. This example is called CH or CC coupling and can provide additional structural information, but it's really not something you need to worry about for the MCAT. And just to start assigning a little bit of practice here, the number is corresponding to which carbon it is. So a good rule of thumb is the farther left, the more oxygen-y, the more oxidized this carbon is going to be. So we look and we see, okay, C2 is bound to the oxygen. That makes sense. And usually for the MCAT, that'll be enough to get your point. The rest for, 3 and 4 and 1, I think, okay, 1 and 4 are going to look really similar to each other because they're both CH3s. So I'd say, what are the 2 lines that are closest to each other? Oh, it's these 2. So I bet one of these is C1, the other is C4. And to figure out which one is going to be further to the left, we want to say, okay, well, which of these carbons is closest to the most oxidized thing? And we see, well, this carbon 1 is really close to this carbon bound to an oxygen. So I hypothesize that, okay, carbon 1 is probably the one further to the left. And carbon 3, we know that this is not oxidized, so it's going to be further to the right, which is labeled C3 here. So that's sort of the problem solving you want to do for the MCAT. You don't have to be perfect on this. If you can just remember further to the left, more oxidized, you're probably going to get it right. Now let's apply this knowledge to an MCAT style problem. Imagine an unknown organic compound produces the following 13C NMR signals. One's at 28 ppm, one's at 68 ppm, and another is at 172 ppm. What functional groups do you think are probably present in this compound? Well, let's analyze each signal here. So remember the 0 to 50, that is our classic alkane. So we're going to say that this 28 is more than likely an alkane. 68 is consistent with either an alcohol or an ester, and the 172 ppm is probably a carboxylic acid or ester. So then we'll look at our answers. Well, alkene is not an alkane. I don't see aromatic rings anywhere. We saw ester twice. We didn't say anything about an aldehyde. So the answer to this question is, it is most likely an ester in here. Carbon-13 NMR spectroscopy is a powerful complement to hydrogen NMR for determining the structure of organic compounds. While not as tested as often as H-NMR on the MCAT, understanding the principles of 13C NMR, such as chemical shifts and signal intensity, will help you get way more questions right on spectroscopy, as well as help you with those 2 to 3 C-NMR specific questions you might see on the MCAT. Thank you so much for watching our video on 13C NMR, and I'll see you next time.